Hello everyone and welcome to the first lecture of the 2025-2026 year with the Machine Learning Society. Today I'm going to be teaching you how to use linear regression, and I'm going to be covering the background knowledge to be able to understand everything that's going on under the hood, and then I'm going to be giving you a practical implementation with Pytorch. Everything that we're going to be doing today is going to be done from scratch so that you understand what's going on under the hood, but in real life you might want to use some built-in libraries that implement all of this so that you don't have to repeat it as I'm doing. But let me know if you've got any questions at the end of the implementation, and I hope you enjoy the video. Today we're going to be covering linear regression. In linear regression, we are trying to predict an output, which we call y. And to predict the output, we use our data set, which corresponds to some inputs that we call x1, x2, and x3. And we fit a linear model to trying to make our predictions as accurate as possible. And we do so by comparing it to our data frame. So the way in which we do that is we define our y, which is our output. We define our x, which is going to be our input. And here, as you can see, it's a column vector of x1, x2, all the way up to xn. And y is going to be in this case, our prediction for y is going to be a linear model, which is going to use some weights, which are all these betas. We've got beta 0, beta 1, beta 2, all the way up to beta n. And we've got n inputs, which are the x1s, x2s, and x3s. And x4s and all the way to xn, right? And we've got n plus 1 weights for this model. And, well, we can rewrite it in this form, right? So it's just simply multiplying by the weights and adding all of our products here. And there's this little trick that we can do in which we introduce a new input, which is equal to 1. And now, if you think, our beta 0 is simply multiplying that 1, right? So we can write our y, which is our output, in this form. This is just a way to include beta 0. All right. Now, as you can see, equivalently, we can write this in matrix form. So x is simply our column of x's, and betas are parameters. And if we do this dot product, we obtain y. And here you can see what everything looks like. And here's our linear model. Now, what we want to do is we want to estimate those weights, right? And to do that, we have to define a loss function. And this loss function is going to be telling us how good our model is. So we want the loss to be as small as possible. And in this case, we're using the mean squared error, which takes the difference between our predictions, which is this matrix product, and our real value y, squares them, and then divides them by a value n. Sorry for the video quality here, I did go slightly out of frame. So I'm just going to show you what this looks like for a simple case. We can imagine that y is a very simple model with no intercept, just is equal to b0 times x0. And this is what our loss function is going to look like. So on the x-axis, we've got beta, and on the y-axis, we've got our loss. And we're trying to minimize this loss. So we're trying to choose the optimal value of beta, right? And so you might notice, if you've done a class of calculus before, that the point at which this error is minimized is the same point at which the derivative of the loss function with respect to beta is equal to 0. The derivative in this case is just the slope of the curve. So because the slope is flat, we say that the slope is equal to 0. And this is just a way of writing our loss function using matrix form. This is exactly what you saw earlier with the sum notation. And the derivative of this function with respect to beta is going to be this expression over here. And we can equate this to 0 to find the minimum of our function. And if we find beta in this way, we obtain this expression. This is going to be our optimal beta. And here you've got the loss function once again. And the reason why we can find this optimal beta is because our loss function is convex. What does this mean? Well, if you look at this loss graph over here, you'll see that if we draw a point A up to a point B, our lines always will fall within this parabola. They don't go outside. And this means that we can find an optimal minimum in this function, and we know that our value of beta is the optimal minimum to reduce the mean squared error. We could also do this by gradient descent, in which we would update beta to a value of beta minus a learning rate, and we would multiply by the partial derivative with respect to beta at that point. And this would work as well. And if you want an insight into why this works, you can see that when we take the partial derivative of beta, when we take the partial derivative of the loss function with respect to beta, if that is equal to 0, beta just gets mapped onto itself, which also corresponds to the optimal beta. And for reference, usually we set the learning rate to be between 0.001 and 0.1. During our implementation, I'm not going to show the gradient descent approach, but if you want to give it a go, you're very welcome to do so. And if you're a member of the Machine Learning Society, you can share the code and we'll put it into a repository and you can get credit for that. I'm going to put some of these concepts into practice, and the best thing that I think you could do is just to get your hands dirty. So I'm going to get Yahoo Finance just to get some data set, right? And I'm going to get some libraries that I use every now and then, Pytorch. And also I have created a plotting library for some of the results that we'll be getting later. We've got plot, operations, plotting, and we've got plot residuals. All right, so this is the libraries that we will be using. Let's make sure that everything runs just fine. All right, this is great. So the first thing that we're going to do is we are going to download our data, and for this example, we're going to use the prices of silver. We're going to do gold, and we're going to do oil. And the idea is going to be to use silver and oil to predict gold, right? And we have our data, and we can just call the Yahoo Finance API, just download the data, and it's going to be the tickers, and we can do a start date, which can be it can be anything you want, right? Let's do 2010 and the 1st of January, and the end date, which will be 2025 and the 1st of January, right? So we can just run that, and we can see what it looks like. And here we have a bunch of data, and it includes the closing prices of gold, silver, and oil, but also the highest price of the day, the lowest, what the price at which it opened, and how much volume was traded. For these specific examples, since we wanna keep it simple, I'm just gonna take the close prices. Okay, so prices is equal to data, and here we have the column which is called close, right? So we just select this column, and we can visualize what this looks like. Here's an S. There you have it, right? So we're gonna be using gold and oil to predict silver, right? So let's see how we're gonna do this. Well, the first thing to do is to convert the close prices to NumPy, because we're going to be multiplying matrices like I showed you in the example earlier. So pandas, it's not really suitable to do that. So I'm going to convert it into NumPy, and I will actually convert the data to Pytorch later on, since it's the machine learning library that I use the most. So we convert it to prices, and as you can see, this and this is exactly the same, right? 109, 109. It just it's just a different data type, right? And what we can do now is to create our data set. So if we're using gold and oil to predict silver, we have to join these two columns, right, into a single data set. So we can just go concatenate, and this is going to take prices. So we're going to take the first column, which has index 0, and we're going to take the second column, which has index 1. And let's see, and we have to define the axis, right, which is equal to 1. And y, which is the variable that we're trying to predict, which is the oil, simply going to be the prices here. Let's see. Okay, and we have an error right here. Let me read this. Okay, yeah. Let's see. This actually should have been 2 from the start. Okay, this runs. And we have our X data set, which has the first column, which is here, the second column, that looks right. And let's look at our Y variable. Yeah, that's fine. And we can have a look at the shape. This means that we've got 3,774 observations, which makes sense roughly for 10 years worth of data. And we have 2 features. And we can also look at the shape of Y, and it has the same number of observations, but only 1 feature, which is the feature that we are trying to predict. Okay, so that's great. That does make sense. Now what we're going to do is we're going to convert this into a torch tensor. And it's very simple. We just put X, and we're going to specify the data type, because when you do like mathematical operations with Pytorch, Torch expects that you're multiplying the same data types, right? So I'm gonna use torch.flow32, and for Y we're gonna do the same. Tensor Y data type torch.flow32. All right, that is great. And now, as you remember from the explanations, our X matrix is going to have a column of zeros, which are representing the intercept. So let's just add this now. So with Torch, this is very simple. We can just create the let's call it the intercept, right? Let's just torch.ones. And the shape of these torch.ones has to be, it's going to have to be yeah, x.shape 0, right? Which I believe this should be 3,700 and something. You have it, right? So this is how many ones we're getting. And we just have to make sure that it's a 2-dimensional array. So we add this one, and we can have a look at what our intercept looks like. And it's just a column of ones. And now what we do is we just add this to our data set, right? To our X array. So we just join the columns, and we're going to join the intercept and our current frame, and we're going to do it along the first dimension. And if we look at what this looks like this now. So this would be our gold price. This would be our oil price. And this right here is just our intercept. Remember, this is going to be multiplying B0. So right now we're going to have the equation is going to be something like Y is equal to 1 times B0. This is the 1 plus the first price, which is X1 times B1, and plus this is the X2, right? So X2 times B2. This is what this looks like. All right, so now we can, I can just give you an example, right? Like if we define our intercepts, let's call it tensor, and let's just pretend, I don't know, I'm just going to make up some weights now, right? To 0.1. And remember, it has to be the same data type. So the data type is a torch.float32. So if we look at what our B looks like, these are weights. And now we can do matrix multiplication on our X matrix and the weights, and we get a bunch of predictions. And just for comparison, these are the real values, right? So right now our model with random weights is predicting that on our first observation, which represents passing this onto the model, we are obtaining 54. The real value should be 17. This is expected because we should be optimizing those weights, which is what we're going to do right now. And actually, something that we can do to measure the error is to define the mean squared error, which we defined earlier. And to do this, we just need to pass our X, our weights, and our real values, right? And so we have our Y hat, which is our prediction, which is going to be X multiplied by B. We have our error, which is going to be Y minus Y hat. And then we can have our error squared, which is going to be the square of the error, right? Just like this. And then we can have our, well, we have to add up all of these errors, right? So the total error is going to be the sum of these errors. We're adding everything up, so we don't need to specify the dimension here. And we are going to return the total error divided by the total number of observations, which is just x dot shape 0, as I showed earlier. So this is our mean squared error. So if we pass values into this function, it's going to tell us how good our function is, or how good, sorry, our linear regression equation is performing. So for the x, b, and y that we currently have, this is our mean squared error, which is, let me zoom in a little bit. It's approximately 2,600,000 units, right? So it's not very good right now. Maybe if we, let's say that this is equal to 12, I don't know, just making this up. Our mean squared error is even worse now, something to the power of 10. So as you can tell, we're trying to find the optimal B. So if, like, just from the explanation from earlier, this is simply defined as, let's call it B star, and this is equal to going to be the inverse, this, of X transpose multiplied by X multiplied by X transpose multiplied by Y. These are perfect B. Now we can call the mean square error function again. And if we call it with B star, we get the mean squared error of 9.5, which is better than these millions of units, right? And now what we can do is we can just plot the predictions, right? So we've got these functions here. So we've got the prediction versus observations. So we can plot this and this function. See, it takes a y, prediction. And let's see what else it takes. And that's it. Oh, sorry, yeah, we have to define a prediction, right? So our prediction is going to be equal to x b star. So if we plot this, sorry, this is what it looks like. So in our x-axis, we have our observed values. These are the ones from the data set. And in our y-axis, we've got the values that we're actually predicting. So the red line would be the ideal fit. What this means is that, well, if the actual value is 20, we would like to predict 20, right? So everything that diverges too much from this line is not very good. But as you can see, our observations fall somewhat close to the line, which means that our linear regression model seems to be working just fine. Then we can do some feature plotting. So we do that. So we have to specify our x, our b star, and our y. And when we use a linear model, we do get a hyperplane. A hyperplane is It's a geometric object that divides our space into two spaces. So we've got 3D space, and we can see that this divides it into two sections. In the case of a 2D model, we have a simple line that divides a 2D space into two sections, right? So our red dots are the predictions that our model is making. As you can see, they fall on the this plane, and our blue dots are our actual observations here. And here we can see our predictions versus our observations with respect to both features. And here is just like 3 different observations with respect to the plane. And one thing that's important to do as well is to predict our residuals. And our residuals are simply the difference between our predictions and the actual values from the real data set. So we've got this third function here, which is called plot residuals. We're just going to take it. And this function takes y, our y prediction, and takes our x. And here you can see our residuals. So if the residuals are equal to 0, that means that the difference between our predictions and the real values are the same, right? So obviously you want stuff that's very close to 0. And here is the residuals for the model overall. And here they are with respect to both features. And here you can see 3-dimensional space, but this maybe is not very clear. And yes, this has been a practical application on how to use linear regression. If you've got any questions, please put them in the comments. And yeah, just one more comment. I have not decided to cover the gradient descent implementation, but if you want to try it and implement it, you're very free to do so. And if you do a good implementation, we'll be very happy to just put it on our GitHub and to give you credit for it. So this has been everything, and I do hope that you enjoyed this session. Bye-bye.